final reaction we're going to look at with alkenes is called an ozonolysis. And this one is a bit different than the others because we're not just adding something across the double bond, but we're actually cleaving the double bond. We're breaking it in half. And the reagent that we use for this is ozone, which is O3. And we'll look a bit more at its structure in just a moment. So in general, what's happening here, we're taking a double bond, subjecting it to oxidative conditions, and a common way that oxidations are abbreviated is just an O in brackets. And we're breaking this double bond. And what will happen, each of these carbons that were part of the double bond now becomes a double bond to an oxygen. So we get one double bonded to an oxygen, and we get a second double bonded to the oxygen. And these are the two carbons that were part of the alkene. We're going to take a look at two variations of the ozonolysis. The first involves a reductive second step. So we actually do the oxidation step, and then we add a reducing agent at the end of the reaction. Let's look at an example of this. We're going to start with an alkene. And we're going to subject this to ozone in step 1. And then step 2, I'm going to use DMS. DMS is dimethyl sulfide. You can also use zinc and an acid source as the reductive second step. If you see either DMS or the zinc and acid, it means the same thing as far as the products. So when we do this reaction, again, think about breaking right across this double bond. And we're going to have two carbons. We have this carbon and this carbon. Each end up double bonded to an oxygen. So if we draw the fragments that we get out of this, we have our cyclopropane, so that's the carbon in blue. And instead of the double bond to another carbon, we end up with a double bond to an oxygen. The second product, we have a 3-carbon chain and our carbon in green, and that ends up double bonded to an oxygen as well. So with this reductive second step, none of the atoms change. We're just cleaving across the double bond and adding a double bond O in the products. Specifically, on this carbon in green, there's a hydrogen here that was implied, and that hydrogen is still present. And that's really important in this reductive second step. If your second step is reductive, the hydrogen on an alkene remains, and you end up with an aldehyde product. So in a sense, there's really no major changes to the structure other than breaking the two carbons apart. Next, we're going to look at an oxidative second step. And just to give you a preview, what's going to happen in the oxidative second step is this hydrogen is going to get oxidized to an OH group. So here we're going to look at the oxidative second step. I'm using the same alkene starting material as we did in the previous example. We're doing the ozonolysis, followed by, now instead of a reducing agent, we have an oxidizing agent, hydrogen peroxide. In this case, we still have our two carbons to focus on. And And for the carbons of the double bond that just has carbons attached, nothing changes with this oxidative second step. We're going to get the same product. We're going to cleave across that double bond, just like we did before. And this carbon that has the blue dot ends up double bonded to an oxygen. But now for our second product, we have the 3-carbon chain and the carbon that I highlighted in green. That carbon also ends up double bonded to an oxygen. But the main difference here is under these oxidizing conditions, this hydrogen gets oxidized to an OH group. So we're changing that H to an OH in the product, and we get a carboxylic acid. An alternative set of conditions for this that you might see, it's no longer an ozonolysis, but it gives the same products if you use potassium permanganate and acid. So just bear in mind, if you see the oxidative second step or the potassium permanganate, the hydrogen on the alkene becomes an OH to give a carboxylic acid. Let's take a look at a couple of examples here. In this first one, we have a diene, meaning we have 2 alkenes in the starting material. Well, when you add ozone, this is going to be a gas that's going to be in excess, so you can't really just selectively do one of the double bonds. If you add it, you're going to oxidize both double bonds. So we're going to cleave this here and here. So if you need to, just redraw your starting material. I'm going to extend the double bonds just a little bit to give us some space. So this is just one strategy you can use. And really all you're doing in this cleavage is erasing through those double bonds. So I'm going to take my eraser, erase through those, and then add an oxygen to each end. An O here, an O here, here, and here. I'll clean it up just a little bit so it's easier to see. Here's our 2 products. And in this case, we had a reductive second step with DMS. So these hydrogens that were on the alkene, like this one here, nothing happens to it. It just stays a hydrogen, and we end up with aldehydes. In the second reaction, it's a little different in that we have this alkene within the ring, and when we cleave it, it's not going to actually break this into 2 molecules because the ring tethers the 2 pieces together. So because we have this oxidative second step right here, I'm going to draw in my hydrogen on the alkene just to keep track of what happens to them. We're going to cleave at this double bond, and then the products we get, just going to separate that a little bit here just to help you keep track of things. Let's make 1 carbon green, 1 carbon orange. That's those 2 carbons. So the green carbon, we end up with a double bond O, and that hydrogen now becomes an OH group under the oxidative conditions. On the orange carbon, we get a double bond O as well, and that has just the ethyl group attached. So that's the product. It's totally fine to draw it just like that. If you want to clean it up and make more of a zigzag chain, you can do that. It's the exact same thing. It doesn't matter which way you draw it.